And with the help of Fleming's left hand rule, we discuss how to find out the direction of the force on a conductor placed in a magnetic field. And we also consider different orientations, like if we draw the diagram on a flat paper with the concept of into the paper, out of the paper, or if you will get this type of diagram in the 3D form, so still we can identify the direction with the help of Fleming's left hand rule. And the basic purpose, or the principle on which the DC motor actually works, so it works on the principle of current carrying conductor in a uniform magnetic field. And we also mentioned the components we used in DC motor. Permanent magnet coil is a very basic component for us. We already know about it. So the components like carbon brushes and split ring commutators, these are new or the type of component that we study for the first time in electromagnetism. And now, if we solve some questions from the past papers, so let's see how many questions we will get from this topic of DC motor. Okay, so from 2023, we have first question related to DC motor. It shows single turn coil of a simple DC current motor. Explain the direction of the turning effect as seen by an observer at O. So let's suppose we are observer at this point O, and we are observing this coil from the front. And this is the direction of current moving into the paper. So current is moving into the paper, and the direction of magnetic field is from right to left. Because in this diagram, we have north pole on right side, south pole on left side. In our diagrams, we normally practice with north on the left side. So you can easily compare with this idea. Now, north is on right hand side, south is on left hand side. So first of all, we have to identify the direction of turning effect. So for that, definitely we have to identify the direction of force first. So if we talk about the field, so the magnetic field is towards left hand side. It is moving towards left hand side. Second, if we talk about electric current, so electric current is into the paper. And as we discussed that all three quantities are mutually perpendicular. So basically, if you mark axis, so field is on x-axis, field is on x-axis, and current is on z-axis, because into the paper, out of the paper, that is the third axis in the diagram. Now, the direction of force is unknown. So it is confirmed that the force must be on y-axis, because no quantity from the left hand rule is on y-axis. So definitely this force will be on y-axis, right? So now, if you apply the Fleming's left hand rule, so identify the direction of force on the left side of the coil. Is it downward or upward? Current is going into the paper from this direction and moving outward from the other side. So first of all, you have to open up the first finger towards left hand side, then current into the paper, right? So I will share the picture of orientation also. So if you want to exactly find out the orientation, and according to the diagram, let's suppose if you shuffle the poles, like if we consider north pole on the left hand side and south pole on the right hand side, so we know that force acts in downward direction. You can see in this diagram, force is acting in downward direction. So if we shuffle the poles of the magnet, so definitely the direction of the force also changes. So you can also relate like this. It's up to you. Whatever the method you think that is easy for you, so you can follow that method. Okay. Okay. I also shared the orientation of the left hand rule. So you can also check the orientation of left hand rule. Second finger represents the direction of electric current into the paper, and the first finger is towards left hand side, and you can see thumb is pointing upward. So you can see in this diagram force is downward, but now in this diagram force is upward, and from this side force will be downward. It means this is the pattern of rotation clockwise. So we can say that using Fleming's left hand rule, current is into the paper and force on left side of coil acts in upward direction. Coil rotates in clockwise direction. So this is the direction of rotation of the coil. So you can see from the same pattern of the diagram, sometimes they change the poles of the magnet from right to left. Sometimes they change the direction of current, and sometimes the direction of force will be different. So if you change any one quantity, so definitely the force on the conductor also changes its direction. And further, if we consider the DC motor idea, so there are some factors also. Factor affecting force. on a conductor. So the first factor is if we use stronger magnet. So if we consider a stronger magnet, or if we place a strong magnet in a DC motor, so because of that strong magnet, you will get a greater force on the conductor, right? Because a strong magnet provides a strong force, and that will gives you greater change in the rotation of the coil. So greater the magnetic field, greater the force. And the second factor is number of turns. So in our diagram, for basic idea, we just consider a single coil, right? But in practical DC motor, it not happens like the same, that there will be only one coil. There are multiple turns of the coil available in a DC motor. But just for the reference of the diagram, right now in this diagram, we have only one turn of the coil. But if we consider multiple turns of the coil, so because of the multiple turns of the coil, there will be greater change, or there will be greater change in the force, or multiple coils gives you the concept that multiple field lines are passing through different turns of the coil. So there will be a greater change in rotation of DC motor. So increasing the number of turns increases the force on the coil. So basically, this is another factor that increases the rotation of the coil. Rotation of the coil or force on the coil both makes the same sense, because if there is a greater force, so then there will be a greater rotation in the coil. Okay. Third factor, third factor is current. So basically, if the value of current is high, so because of the high current, we know that it also creates magnetic field around the coil. So the greater value of the current will also produces greater change in the coil or greater rotation in the coil. So that will also increases the rotation or the force on the coil. So the third factor is current. Increasing current decreases voltage and resistance. and it helps to increase rotation of the coil. So this is the third factor. So these are the factors that helps to increase the rotation or the force on a current carrying conductor in a uniform magnetic field. Now, if we continue with the second part of the question, the coil is replaced by an otherwise identical new coil. So the coil given in the diagram is replaced by a new coil with three turns and the same current in the coil. State how the turning effect compares with the turning effect in the first part. So definitely, if we increase the number of, yes. So if you increase the number of turns, so definitely the turning effect also increases. Third part, now we replace with the third coil, and the third coil is exactly same like the first one, except that its resistance is three times greater. Then potential difference is also same, just like in the first part. Now, what is the difference between the turning effect as compared to the first coil given in the question? So basically, resistance increases by three times and current decreases by three times. So it means when current decreases, so the turning effect of the coil also decreases. Okay, this part is related to AC generator. So this is 4 mark question from DC motor, and there are some more questions from it. Okay, this is related to transformer. Okay, from this question, starting part is from the transformer topic. So if we ignore the first part and consider the second diagram, because that is related to DC motor or DC concept. So in figure 10.1, it shows a loose wire connected in a circuit with a DC power supply and a switch. The length of the wire between the two supports is in the magnetic field of a horseshoe magnet. The power supply is switched on and the wire moves down. On figure 10.1, draw an arrow on the wire to show the direction of the current. So this time, the direction of force is mentioned. Wire moves down. So the direction of force is downward. And this time, the magnetic field is into the paper. So again, if we talk about the field, so this time field is on z-axis into the paper, and force is on y-axis. Now the third quantity, current. So it must be on x-axis, like towards right hand side or towards left hand side. Because field is on z-axis, force on y-axis. Now current must be like towards right hand side or towards left hand side. So again, consider the left hand rule. First finger into the paper and the direction of thumb downward. When you open up the second finger, so the second finger shows you the direction of current, and that direction of current is towards left hand side. So this is the direction of current if you use the concept of left hand rule. So if you try using your left hand rule to identify this direction, so you will observe that you are getting the same direction of electric current towards left hand side. I also shared the orientation picture of this left hand rule. So from that you can get idea how to arrange left hand rule according to the scenario given in the question. Now the second part, the power supply is switched off and wire returns to its original position because of the electromagnetic force. It is moving in downward direction, but when we switch off the button it returns to its original position between the magnet. The power supply is then switched on so that the current is in the opposite direction. Now current is in opposite direction, so the question is what happens to the wire. So definitely when we change the direction of current, so if you change the direction of current towards right hand side, so because of change in one quantity, the force on the conductor also changes. It will be in upward direction. Because magnetic field remains same, because poles are not changing, poles are in their original position. So that's why only the direction of force changes because of the direction of electric current. So wire moves in upward direction, and it is current direction. So when we change the direction of current, so definitely the force also changes its direction. Okay, this is another part of question. Let's see the first part. First part is related to magnet. Question number 7, figure 7.1 shows two magnets and the gap between the N pole of one magnet and south pole of the other magnet. On figure 7.1, draw three lines to show the pattern and direction of the magnetic field in the gap. So on figure 7.2 is a repeat of figure 7.1 showing the two magnets. So first of all, we have to draw three lines to show the pattern and direction of magnetic field. So it is very simple. Magnetic field always flows from north to south pole like this, north to south, north to south. Now we have same type of diagram in 7.2. Draw the position of a plotting compass needle when it comes to rest in the gap between the north pole and the south pole. So we have to show the position of the compass. So let's suppose if we place compass in the center of these two magnets. So the compass or the needle of the compass shows the direction of magnetic field from the north side. It will be like this. So it is pointing towards the south pole. It means starting from north, moving towards south. Okay. And second part is explain why the needle comes to rest in this position. So what is the reason why needle comes to rest in this diagram or in this field? Okay, so basically, in this diagram, we know that magnetic field flows from north to south pole, and when we place compass in the middle, so there is a uniform magnetic field when we place compass at a fixed point. If we are continuously moving compass at different point, so because of the movement of the compass and at different point of around the magnet, there will be a different type of magnetic field. So that's why if we place compass at a specific point, so that will provides you a uniform magnetic field. So when compass is in rest state, its needle follows field line from the north pole to south pole, and the position shown represents uniform magnetic field. So when there is uniform magnetic field between the poles of the magnet, so there will be no change in the position of the needle. And this question is no more the part of new syllabus, magnetization and demagnetization method. Okay, in the same way, the next part of B part. So in this B part of the question, it shows a simple DC motor, again the same pattern with a split ring commutator. State and explain the direction of rotation of the coil as seen from point X. So again, if we observe from point X, so this is the same type of question. So we have to write statement and explanation. So according to the diagram, this is the positive terminal of the battery, this is the negative terminal. So this is the direction of current. It is out of the paper from left hand side into the paper from right hand side. So it's up to you. You can consider any one direction, left or right, it's up to you. So for example, if we continue with the left hand side, so on left hand side, the direction of current is outward. Current is out of the paper. And magnetic field is from north to south, from left to right. So it means that the force will be again on y-axis, either upward direction or downward direction. So by using the left hand rule, so current is outward, like the second finger is pointing towards ourselves. So if you open up the finger, so you will observe that the second finger is pointing towards yourself and the first finger is pointing towards right hand side, and the direction of force will be upward. So that is the direction of Fleming's left hand rule. So explanation will be the same. Statement direction of force is upward from left hand side and downward from right hand side. So rotation is again clockwise. Clockwise rotation. And explanation is simple. Current is moving out of the paper and field line is moving towards right. So again, by using Fleming's left hand rule, force acts in upward direction. Okay, now the coil rotates through 90-degree from the position shown. So what happens to the moment in the position? So this is the position shown in the diagram. And if we rotate 90-degree, so 90-degree means now it is horizontal. So when we rotate 90-degree, it becomes perpendicular, right? So now the question is, state what happens to the moment in the position. So basically when the coil becomes perpendicular, so in perpendicular there will be no current passing through the coil and there will be no force acting on the coil. So it rotates because of inertia, like in the same direction. Okay. So there will be no current because in perpendicular condition there will be always a gap in the commutator. As you can see, there is a gap in commutator. This is for 90-degree rotations. So when coil rotates, so at 90-degree, always remember at 90-degree there will be no current passes through coil, and coil rotates because of inertia. Because initially it is rotating with the help of the force, and afterwards it will continue the rotation because of that force. So that is the concept of inertia. So basically, itself at 90-degree there will be no force acting on the coil. Coil rotates inertia. Third part, the coil is rotated through 180-degree from the position shown. By considering the forces on the coil, explain how a split ring commutator enables the motor to turn continuously. So this is the same idea as we discussed when we rotate through 180-degree. So 180-degree means, let's suppose if we mark the sides of the coil, let's suppose this is side A, this is side B, this is side C and D. So after 180-degree rotation, side AB will be on right hand side and CD is on the left hand side. So because of the change in the coil or change on the axis of the coil, the forces remains the same, right? Because after 90-degree, at 90-degree there is no force acting on the coil because there is no current, and after 90-degree the sides of the coil actually flips, but still the direction of current is in the same direction because positive is on left hand side and current is coming out of the paper from left hand side and it is going inward from right hand side. So that's why the direction of current remains same and the direction of force also remains the same after 90-degree change. So after 180-degree rotation, sides of the coil shuffles, but the current is in same direction and force is also in same direction. Only the sides of the coil shuffles and the direction of current, direction of force remains the same. So you will get the same type of question from the DC motor concept, because in DC motor we have a fixed idea, fixed concept of DC motor. Only sometimes they change the diagrams, sometimes change the pole of the magnet, and in some question you observe that they ask question by changing the direction of current, by changing the direction of force. So this type of questions you will get from the DC motor. And we also discuss about the factor affecting DC motor, like if we change the number of turns of the coil, so definitely the rotation will increase. If we increase the current in the coil, the force on the coil also increases. And if we use a strong magnetic field or a stronger magnet, so that will also increases the rotation. Now you can see some questions are also from alternating generator, AC generator. And this is also the same question. Explain the purpose of the split ring commutator. So we discussed in the notes, split ring commutator helps to flip the direction of current in the coil when coil crosses the vertical position. And why vertical position? Because in vertical position we discussed in previous part that at vertical position there will be no current. So when there is no current, so no force is acting on the coil, and coil rotates because of inertia, not because of force. So that is the concept of split ring, right? So these are the type of question related to the DC motor concept.